Good evening. I am Professor Shalini Sahay from EC department, going to introduce the type of system through this lecture. Firstly, I will define what is system. So a system is a collection of one or more devices, processes, or computer implemented algorithm that operates on an input signal X and which produce an output signal Y. Now, when the input and output are continuous time signals, then the system is known as to be continuous time system or an analog system. And when the input and outputs are discrete time signals, then the system is said to be discrete time systems. Mathematical models of the systems are very useful because they allow us to analyze, design, and predict the behavior of the system. Now, to know the system, first we will discuss some important properties of the system. Causality. A system is causal if the output does not depend upon the future values of the input, and if the output at any time depends only on values of the input up to that time. All real-time physical systems are causal because time only moves forward. Effect occurs after cause. Now, the causality does not apply to spatially varying signals. We cannot move both left and right, up and down. We can move only at a time either left and right or up and down. It does not apply to the system preceding recorded signals. For example, taped sports games versus live broadcast. So we cannot apply causality to the system which are the recorded signals. Some examples of the causal system are like this. We have taken the continuous time signals. This is the discrete time signals. And these examples show the examples of the causal system. Now we'll define the linearity. It is also a very important property of the causal systems. A system which is linear, it obeys the principle of superposition. So what does the superposition theorem states that if more than one signals are acting on a system, then the total response of the system is equal to the sum of the individual responses of the system. So these are the various signals, and which shows that this signal is a linear system. Now, the other property which is more important is the time invariance. A system is time invariant if its behavior does not depend upon the choice of t is equals to 0. Then two identical experiments will yield the same results regardless the starting time. It means that a system whose response does not change with the change in time are known as the time invariance system. For example, if we take the discrete system xn and yn is the response of the system, now what we have done, we have shifted the signal with n minus 0. So the response is also shifted. So this shows that the system does not change with the time. So it is the time invariance system. These are the few examples which shows the time invariance property of the system. Now, when we talk about the time invariance, the property which comes along with is the periodicity. We know that a single signal is periodic, which means that it is repeating after a regular interval of time t. For example, if we take in a continuous time signal xt, so after the shifting the signal to the new time t period, but xt is equals to xt plus t, so we can say that the system is periodic signal. So a basic fact is that if we know the response of an LTI system to some input, for example, sine waves, we actually know the response to many inputs. Now, our main concern is the linear time invariant system. So any linear time invariant system, continuous time system, or the discrete time system can be uniquely characterized by its impulse response, which means that the system responds when we apply the impulse as an input. Second is frequency response of a system, which means that response of the system to a complex exponential e to the power of j2 pi f for the all possible frequencies of f. Transfer function, for example, Laplace transform of impulse response. Now, what is the significance of the unit impulse? Every signal, whether large or small, can be represented in terms of linear combinations of delayed impulses. So the main properties which can be applied on the system is the linearity and the time invariance. For the discrete time or the continuous time cases, there are two natural choices for these two basic building blocks. For discrete time, shifted in unit samples we are taking, and for the continuous time we are taking the shifted unit impulses. Now when we talk about the impulse response, the most important property arises, which is known as the convolution. So this is a fact, together with the property of the superposition and the time invariance, we will allow us to develop a complete characterization of an LTI systems in terms of responses to a unit impulse. These are also called as the convolution sum in discrete time cases, whereas convolution integral in continuous time cases. Now, the response of a discrete time system to a unit sample sequence, which is represented as del n, is called the unit sample response, or simply the impulse response, and it is denoted by the Hn. So we are applying the input as an impulse, and its response is denoted by Hn. The response of a discrete time system to a unit step sequence is called the unit step response. So when we are applying the unit step function as an input and we are taking the output response of the system, which is known as the step response, and it is denoted by Sn. Now, some few examples of the impulse responses. Now, the impulse responses of the system we have taken as Yn is equals to alpha when the impulse is located at 0, and then we have shifted the impulse at n is equals to 1, n is equals to 2, n is equals to 3. So in this, we have what we have done for the various inputs at different regular instant of time, we are multiplying with its impulse, and we are shifting the impulse at that location. Now the impulse response, thus a finite length sequence of length 4, what we have taken the 4 impulses. We have shifted the impulse at 0, 0, it is the position of the impulse. We have shifted at 1, 2, and 3. So we are taking the 4 samples. So its length will be n is equals to 4, and which will start from 0, 1, 2, and 3. Now, the impulse response of the discrete time accumulator we have taken as we are shifting the impulse from -infinity to n. So this is showing the impulse response. Now, the time domain characterization of LTI discrete time system. So a consequence of the linear time invariance property is that an LTI discrete time system is completely characterized by its impulse response. Knowing the impulse response 1 can compute the output of the system for any arbitrary input. Here we have denoted the impulse response of the system as an Hn, and we have computed the output Yn for the various inputs. The system is time invariant. So what we have shown is the impulse we have shifted at 2, so the output response will also be shifted at -2. This is the impulse which is shifted at n is equals to 1. The response is also shifted at n is equals to 1. So the shifted response of the input of the impulse correspond the shifted response of the output. Likewise, what we have done, we have applied the input also, which is multiplied 0.5. We have scaled the impulse. So the output response is also scaled with the shifting operation. Now, any arbitrary input sequence xn can be expressed as a linear combination of delayed and advanced unit samples. So we will introduce it by a function xn, which is equals to summation of k minus infinity to plus infinity xk, and it is multiplied by impulse which is shifted. The response of the LTI system to the input now will be given by the following equation. The representation of discrete time signal in terms of impulses, what we have shown previously is to visualize discrete time signals in terms of individual impulses. Now what we have done, we have scaled the unit impulse sequences, and where the scaling on each impulse equals the value of xn at the particular instant the unit impulse occurs. Graphically, we have also shown like this. This is the impulse and these are the impulse. So this is the input signal. So this is the samples what we have taken as an input. This is the value of input at 0. This is the value of input at 1, 2, 3, -1, and so on. Now what we have done, this input is multiplied by the impulse del n x0. So what will be the output? So its output will be the multiplication of the input with 1. So we will get the output. Now for the input located at 1, what we have done is we have shifted the impulse also at 1, and then we have multiplied. Now again what we have done for the x -1, we have shifted the impulse to the left hand side. So by shifting the impulse and multiplying with its input, we'll get the convolution sum. So mathematically we have shown by multiplying the input with the shifted impulses. So this is also called as the shifting property of the convolution. Now this property corresponds to the representation of an arbitrary sequence as a linear combination of shifted unit impulses, and where the weights in the linear combinations are xk. Now what is the significance of this property? It is the scale version of very simple set of elementary functions, each of which is non-zero at a single point in time. Moreover, property of time invariant states that the response of a time invariant system to the time shifted unit impulses are simply time shifted version of another. So this is the property which we have shown with the help of the mathematical function, and this is applying the superposition theorem. Now this is the impulse as an input. This is the output response. We have shifted the impulse. The response is also shifted. So for an LTI system, this is the convolution sum. So the last equation is called the superposition sum or the convolution sum. So it is the convolution property which is completely characterized by its response to a single signal, namely its response to the unit impulse. Thank you.